Imagine particles traveling for millions of years, crossing unimaginable distances, only to arrive right here on Earth. These are cosmic rays, and they carry secrets from the universe's most violent events. What profound messages do these ancient travelers bring from the very edges of existence? Every second, tiny, ancient particles from across the cosmos are zipping through you, through everything around us. They've witnessed black holes, supernovas, and the birth of galaxies. Discover how these invisible messengers are profoundly reshaping our understanding of the universe's most extreme phenomena, right here on your planet. What if the most powerful events in the universe are constantly sending us direct messages? Cosmic rays are not just random particles, they are relics from the universe's most spectacular explosions and extreme environments. Join us as we decode the incredible journey of these cosmic messengers and what they reveal about the fabric of reality. Hook. Imagine particles traveling billions of light-years to reach your eye, the ultimate cosmic message in a bottle. As you picture this, think about the almost impossible journey these particles endure, crossing the vast darkness of intergalactic space with nothing guiding them except momentum set in motion long before Earth even existed. Each particle carries within it the memory of ancient events, exploding stars, colliding galaxies, or quantum fluctuations near unimaginable cosmic phenomena. When one finally arrives and touches your eye or a detector, it is as if the universe has whispered a secret across eternity, delivering a fragment of a story too immense for our limited senses to fully comprehend. These particles embody a form of cosmic storytelling. They are not merely bits of inert matter or radiation, they are physical messengers shaped and accelerated by extraordinary forces. Their paths are bent by gravity wells, altered by magnetic fields, and stretched by the expansion of spacetime itself. The fact that they remain coherent, detectable, and meaningful after such a journey highlights the remarkable resilience of natural laws. Every time one of these messengers is captured by our instruments, it adds a new piece to the grand puzzle of cosmic evolution, granting scientists insight into events too distant and ancient to observe directly. When these particles originate in environments like supernovae or active galactic nuclei, their energy levels can dwarf anything produced on Earth. Their staggering power acts as a cosmic signature, identifying the violent origins that forged them. These high-energy particles reveal processes far beyond what human technology can replicate. The universe, through them, shows us extremes that shatter intuition. Temperatures millions of times hotter than the sun's core, shockwaves traveling at relativistic speeds, and magnetic fields so intense they twist space itself. All of this becomes knowable because a single particle survives its impossible odyssey. As they travel, these particles interact with almost nothing, gliding through interstellar gas so thin it might as well be empty. This near-perfect isolation allows them to preserve their integrity for ages. Unlike light, which can be absorbed or scattered, these messengers often pass unhindered through galaxies, nebulae, and dark matter halos. This quality makes them invaluable to astrophysicists, acting like probes capable of traversing regions opaque even to the finest telescopes. Their survival through cosmic voids becomes an encoded record of where they've been and what forces they've encountered. By the time these particles finally approach our solar system, their speed may be so immense that they carry more kinetic energy in a single unit than a fast-pitched baseball. The Earth, unaware of this bombardment, sits silently as trillions of cosmic particles stream in every second. Most pass through unimpeded, but a select few collide with atoms in our atmosphere, creating cascading showers of secondary particles. These showers fan out like invisible fireworks, briefly illuminating the sky with information our eyes cannot detect but our instruments can decode with extraordinary precision. When a detector registers one of these events, it does more than capture a moment, it captures a legacy. The collision yields clues about the particle's energy, mass, and direction, enabling scientists to work backward through spacetime and estimate its origin. This reverse mapping transforms an invisible point-like event into a cosmic breadcrumb trail. The data reconstructs not only where the particle came from but what cosmic drama propelled it across unimaginable distances. It is as though the universe gifted us with a documentary filmed across billions of years, frame by frame, particle by particle. Even more intriguing is how these particles challenge our understanding of physics. Some possess energies that defy conventional theories about how particles should behave. They stretch accepted boundaries, forcing physicists to reconsider assumptions about quantum mechanics, spacetime structure, and the limits of natural acceleration. Each anomalous detection is like a puzzle piece that doesn't quite fit, hinting at deeper layers of the cosmic blueprint waiting to be discovered. Through these rare outliers, nature invites us to expand our imagination and refine our scientific frameworks. As detectors become more advanced, they begin to pick up subtler patterns in the flow of cosmic particles. Scientists notice clustering in certain directions or seasonal variations tied to Earth's orbit around the Sun. These patterns reveal that Earth does not simply sit passively in the particle stream, it orbits through currents, waves, and gradients of cosmic messengers shaped by galactic magnetic fields and the structure of the Milky Way. Each shift in the data reflects a shift in our cosmic environment, transforming Earth into a ship sailing through an invisible, ever-changing ocean. In this ocean, not all particles are created equal. Some are tiny neutrinos, nearly massless and capable of passing through an entire planet without slowing down. Others are heavy atomic nuclei accelerated to energies that dwarf even the strongest particle colliders humans have built. The variety of particles ensures a variety of stories. Some recall starbirth regions where young suns ignite, while others recount tragic endings when massive stars collapse under their own gravity, triggering vast cosmic explosions. Each class of particle offers a unique perspective on the life cycles of celestial bodies. Some particles originated long before the Sun existed. They began traveling when the universe itself was younger, denser, and more chaotic. They have watched galaxies collide, black holes merge, and interstellar civilizations rise and fall if such things exist. Their journey is not measured in miles but in epochs. When such ancient travelers finally encounter Earth, they offer us a glimpse of what the cosmos looked like in its formative stages, delivering a message written in energies rather than words. When one of these messengers reaches your eye, it may interact with a single molecule on your retina, triggering a cascade of biochemical reactions that your brain interprets as light. It is astonishing that something birthed in a distant star's explosive death can end its journey by gently activating a human neuron. This intersection between cosmic violence and delicate biological processes highlights the deep interconnectedness of the universe. The extremes of astrophysics converge with the subtleties of human perception, linking us to distant galaxies through invisible threads of energy. Scientists often describe these particles as cosmic rays, though the term is somewhat misleading. They are not rays but individual particles, each following its own path. Yet the poetic name remains because it captures the drama of their journey. They are rays from afar, streaks of energy slicing across the void. Their arrival on Earth is a reminder that our planet is not isolated but bathed constantly in evidence of cosmic activity. Our atmosphere glows with their influence, our magnetic field bends their trajectories, and our instruments listen for their whispers. Some detectors are buried deep underground or beneath ice sheets to shield them from background noise. When they capture one of these elusive particles, it is like finding a needle in a cosmic haystack. The surrounding rock or ice filters out everything but the rarest, most penetrating messengers. Their detection is not merely a measurement but a revelation. It affirms that the universe still holds mysteries that require patience, creativity, and monumental engineering to uncover. In the vast stillness of space, these particles race forward at nearly the speed of light, carrying with them the imprint of their birth conditions. Their energies encode the turbulence of shock waves, the curvature of space-time, and the architecture of cosmic magnetic fields. When scientists unravel these clues, they piece together a story that no telescope could ever capture. Telescopes show us what the universe looks like. These particles show us how the universe behaves, revealing physical processes hidden behind veils of light and dust. Even distant black holes contribute to this cosmic torrent. As they consume surrounding matter, they unleash powerful jets that fling particles across the stars. These jets slice through space like cosmic lighthouses, marking the locations of some of the most extreme environments known to science. When such particles reach Earth, they bring with them signatures of the monstrous gravitational engines that launched them, helping scientists probe regions where the known laws of physics strain to remain coherent. Some particles come from phenomena so rare that scientists classify them as cosmic anomalies. These anomalies ignite global collaborations, uniting observatories, satellites, and underground detectors in pursuit of answers. Each detection becomes a spark for new research, new theories, and new possibilities. In this way, the particles act not only as messengers from the cosmos but as catalysts for human curiosity, driving science forward as we seek to comprehend the universe's deepest mechanics. As technology improves, scientists begin to imagine future detectors capable of interpreting even fainter and more ancient messages. The dream is to build instruments sensitive enough to capture particles from the earliest epochs of cosmic history, perhaps even from the first seconds after the Big Bang. Such particles would reveal conditions that no telescope could ever observe directly, peeling back layers of cosmic time like pages of an ancient manuscript waiting to be read. Yet even with current technology, each particle teaches us something extraordinary. Their interactions with Earth's atmosphere, magnetic field, and detectors highlight the complex interplay between celestial and terrestrial physics. We learn not only about distant galaxies but about our own planet's protective layers, its place in the cosmic environment, and its ongoing relationship with the universe beyond. Earth is constantly shaped, in subtle ways, by these incoming streams of energy. The idea that particles can cross billions of light-years and remain intact underscores the fundamental stability of natural laws. Gravity, electromagnetism, and quantum interactions remain consistent across the universe's vastness. This consistency allows us to trust the stories these particles tell, confident that the physics governing their journey is the same physics we study in laboratories. In this way, cosmic messengers bridge the gap between the incomprehensible scale of the universe and the measurable precision of human science. Their arrival also reminds us of our cosmic vulnerability. If particles of such staggering energy can reach us effortlessly, it follows that the universe remains dynamic, unpredictable, and capable of producing forces far beyond human control. Yet this vulnerability carries a strange beauty. We are part of a much larger story, embedded in a cosmic network that extends far beyond our galaxy. Every detected particle is a small but powerful reminder of our connection to the deep, ancient universe. Ultimately, these particles represent one of the universe's most extraordinary gifts. They deliver knowledge across distances so great that even light takes billions of years to traverse them. They bring us evidence of events we cannot witness directly and phenomena beyond our technological reach. And perhaps most profoundly, they remind us that the universe is not silent. It speaks constantly through these tiny messengers, scattering its history across the cosmos in the hope that curious minds might one day listen. What exactly are cosmic rays? Introduce them as high-energy particles, protons, atomic nuclei, from beyond our solar system. These particles, though tiny, carry immense energy and arrive at Earth from distant regions of the Milky Way and beyond. They are not rays in the classical sense, but discrete, individual particles traveling at nearly the speed of light. Their small size disguises their importance, for each one is a relic of cosmic events of extraordinary power. They come from supernovae, stellar winds, black hole jets, and other environments where matter is accelerated to extreme velocities. Their presence on Earth serves as a constant reminder that our planet is immersed in the energetic currents of the larger universe. At their core, cosmic rays are dominated by protons, the simplest form of normal matter. These protons make up the majority of the flux that reaches Earth, but the remaining portion is composed of heavier atomic nuclei like helium, carbon, oxygen, and iron. The fact that these heavier nuclei survive their interstellar journey without being stripped apart reveals the stability of matter even under immense stresses. Each atomic nucleus that makes the trip carries a chemical fingerprint of the astrophysical process that forged it, enabling scientists to reverse engineer the environments where they were created. Despite their name, cosmic rays are nothing like beams of visible light. Light is a wave, while cosmic rays are particles. This difference allows them to interact with matter in unique, powerful ways. When they collide with atoms, they release bursts of energy that far exceed those from typical electromagnetic interactions. Their particle nature also enables them to be deflected by magnetic fields, which means their paths rarely remain straight across interstellar space. By the time they reach Earth, they have likely taken a winding, chaotic route through the galactic magnetic web. Because of their extreme energies, cosmic rays can cause significant ionization when they strike atoms in the atmosphere. This ionization is crucial to understanding how cosmic rays influence weather, climate, and atmospheric chemistry. The chain reactions they initiate can ripple through multiple layers of the atmosphere, affecting cloud formation and electrical activity. Despite being so small and so distant in origin, cosmic rays can touch entire atmospheric systems, showing how interconnected the Earth is with the broader universe. Many cosmic rays originate from supernova remnants, where shock waves generated by stellar explosions accelerate particles to immense speeds. These shock waves push particles forward repeatedly, increasing their energy each time they bounce across magnetic turbulence. This natural acceleration process is so efficient that it surpasses anything humanity has built, including the most powerful particle colliders. Every cosmic ray detected on Earth is a sample of physical conditions far beyond what human engineering can replicate. Some cosmic rays come from even more exotic sources: active galactic nuclei, pulsars, and gamma-ray bursts. These cosmic engines unleash energies so high that they can hurl particles across galaxies as easily as a child throws a stone across a pond. When such a particle arrives at Earth, it carries with it not just energy but also information about the magnetic fields, shock fronts, and gravitational forces that shaped its journey. As a result, scientists treat each cosmic ray like a messenger, embedding clues about its birthplace within its energy spectrum and composition. Cosmic rays also include a tiny fraction of antimatter particles such as positrons and antiprotons. Their presence raises intriguing questions about the processes that produce them. Are they formed purely in known astrophysical environments, or do they hint at exotic physics such as dark matter annihilation? Even a small increase in the ratio of antiparticles can spark scientific debates, because such anomalies may reveal new or hidden aspects of cosmic evolution. Cosmic rays, therefore, provide an unexpected window into the world of fundamental physics. When cosmic rays penetrate Earth's atmosphere, they collide with gas molecules, generating showers of secondary particles like muons, electrons, and pions. These secondary particles cascade downward in a spreading cone, forming what scientists call an air shower. Some of these particles reach the ground, and a few even penetrate deep underground. This cascading effect underscores the immense energy cosmic rays carry. From a single incoming particle, thousands of new particles are produced in a chain reaction that unfolds in a fraction of a second. Cosmic rays arriving at Earth come in a wide range of energies. Some are relatively low energy and originate from within our solar system, influenced by the Sun's magnetic field. Others are incredibly high-energy particles that travel across interstellar space. The most extreme cosmic rays, called ultra-high-energy cosmic rays, possess energies millions of times greater than anything produced in human accelerators. Their origins remain mysterious, and their detection continues to challenge theories of astrophysical acceleration. The distribution of cosmic rays across different energies forms a spectrum with several distinctive features. Scientists analyze the bends and kinks in this spectrum to identify where different populations of particles originate. For example, one bend, called the knee, suggests a limit to how strongly supernova remnants can accelerate particles. Another bend, the ankle, may signal the transition from galactic sources to extragalactic ones. This spectrum becomes a map of the universe's energetic processes, expressed not in light but in particle flux. Even though cosmic rays bombard Earth constantly, human senses cannot detect them directly. The atmosphere protects us by absorbing the majority of their impact, preventing harmful radiation levels at the surface. However, at high altitudes, such as on airplanes or mountaintops, exposure to cosmic rays increases significantly. Pilots, astronauts, and frequent flyers are exposed to higher doses of cosmic radiation, showing that the influence of cosmic rays extends beyond theoretical science and into the daily lives of those who travel above Earth's protective layers. The discovery of cosmic rays dates back to the early 1900s, when scientists noticed unexpected levels of ionization even in shielded environments. This mystery led Victor Hess to conduct daring balloon flights, during which he found that radiation levels increased with altitude rather than decreased. His observations confirmed that the radiation came from space, not Earth. This discovery opened a new chapter in physics, revealing the existence of particles arriving from beyond the solar system long before humans had any concept of the galaxy's complexity. Cosmic rays played a significant role in early particle physics. Before particle accelerators existed, scientists relied on cosmic rays to study subatomic particles. Discoveries like the positron and muon emerged from cosmic ray research, proving that the universe itself acts as a natural laboratory. These discoveries expanded the standard model of particle physics and demonstrated that cosmic rays could uncover new particles long before human-made experiments were powerful enough to replicate those conditions. The presence of cosmic rays also shapes the evolution of interstellar matter. As they travel through the galaxy, they ionize gas clouds, triggering chemical reactions that contribute to star formation. Cosmic rays help regulate the temperature and ionization balance of molecular clouds, acting as catalysts for processes that ultimately determine where new stars can be born. In this sense, cosmic rays participate in the continuous recycling of matter that drives the life cycle of the galaxy. Cosmic rays are influenced by magnetic fields at every scale: planetary, solar, galactic, and intergalactic. These fields twist and bend their trajectories so thoroughly that tracing a cosmic ray back to its exact origin becomes almost impossible. This magnetic scrambling means that cosmic rays rarely point directly to the source that launched them. Instead, scientists must use statistical patterns, energy spectra, and particle composition to infer where they might have originated. This detective work transforms the study of cosmic rays into a kind of astrophysical forensics. Although cosmic rays are mostly beneficial for scientific discovery, they can pose risks to technology. High-energy particles can interfere with electronic circuits, disrupt satellite operations, and damage spacecraft. They can flip bits in computer memory, leading to unexpected malfunctions. Engineers must design space-based technologies to withstand this constant bombardment, ensuring that cosmic rays do not compromise navigation systems, communication networks, or scientific instruments. These technological challenges highlight the need to understand cosmic radiation in detail. Beyond technology, Cosmic rays may also influence biological evolution. Increased exposure during periods of weakened magnetic fields or intense cosmic events could raise mutation rates. Though such effects are subtle and occur over long timescales, they suggest that cosmic rays could play a small but meaningful role in shaping the genetic diversity of life on Earth. This possibility ties the story of biological evolution to the broader cosmic environment, stretching the concept of natural selection to include interstellar factors. The Sun plays a critical role in regulating the flow of cosmic rays reaching Earth. Its magnetic field and solar wind form a protective bubble known as the heliosphere. During times of high solar activity, the strengthened solar wind deflects many low-energy cosmic rays away from the inner solar system. During quieter periods, more cosmic rays penetrate inward, increasing their influence on Earth. These solar cycles create long-term variations in cosmic ray flux, contributing to changes in atmospheric ionization and even affecting the rate at which radiocarbon forms. Cosmic rays also help scientists study the structure of the galaxy. By analyzing how particles are deflected or scattered, researchers gain insights into the magnetic fields permeating the Milky Way. These magnetic structures are difficult to observe directly, but cosmic rays interact with them constantly. Their behaviors reveal patterns of turbulence, field strength, and spatial distribution. In this way, cosmic rays act as probes, mapping the otherwise invisible scaffolding of the galaxy. Some of the most puzzling cosmic rays are those with ultra-high energies. Their origins defy conventional astrophysical explanations. The energies involved suggest processes even more extreme than supernova shocks or black hole jets. Scientists speculate about exotic mechanisms, the decay of supermassive particles from the early universe, interactions with topological defects in spacetime, or unknown astrophysical accelerators. These particles, though incredibly rare, challenge the boundaries of known physics and inspire new theories about the universe's most powerful forces. Cosmic rays also interact with Earth's magnetic field, spiraling along magnetic lines and becoming trapped in radiation belts like the Van Allen belts. These trapped particles form dynamic layers of charged radiation that surround the planet. While the belts protect the surface from some forms of radiation, they create hazardous environments for spacecraft. Studying how cosmic rays feed into these belts helps scientists build better models of space weather and protect satellites from long-term damage. Even though cosmic rays arrive individually, their collective influence shapes many aspects of terrestrial and cosmic environments. They are constant, ancient, and omnipresent. Their stories span billions of years, their origins lie in the hearts of stars, and their journeys cross the vast gulfs between galaxies. Understanding cosmic rays means listening to the universe's most energetic messengers, decoding the information they carry, and recognizing their role in connecting Earth to the farthest reaches of cosmic history. Where do these particles come from? Introduce the leading hypotheses: supernovae remnants, active galactic nuclei, AGN, and gamma-ray bursts. These three astrophysical giants represent some of the most powerful natural accelerators in the known universe, each capable of flinging particles to near-light speeds. Supernova remnants provide expanding shock fronts, AGN unleash colossal jets from supermassive black holes, and gamma-ray bursts generate explosive bursts of energy that dwarf anything else known. Together, they form a cosmic network of particle forges scattered across the galaxy and beyond, shaping the energetic landscape that floods Earth with cosmic rays. Supernova remnants are among the most widely accepted sources of galactic cosmic rays. When a massive star ends its life in a colossal explosion, it expels layers of gas outward at thousands of kilometers per second. These shockwaves propagate through the interstellar medium, compressing magnetic fields and accelerating charged particles in a process known as diffusive shock acceleration. This natural mechanism boosts particles repeatedly, granting them energies far exceeding anything human-built accelerators can achieve, making supernova remnants powerful cosmic factories. Within the turbulent interiors of these expanding shock shells, particles undergo countless collisions with magnetic irregularities that act like microscopic trampolines. Each bounce increases their energy slightly, but cumulatively, over thousands of cycles, they can reach astonishing speeds. Scientists believe that this repetitive scattering is responsible for producing most of the medium-energy cosmic rays detected near Earth. Observations of remnants like the Crab Nebula and Cassiopeia A show energetic emissions consistent with particle acceleration on a massive scale. However, supernova remnants alone cannot explain the highest energy cosmic rays detected. For those, scientists look to the monstrous engines at the centers of galaxies known as active galactic nuclei. These regions host supermassive black holes millions or billions of times more massive than the Sun. When matter spirals toward these black holes, immense gravitational and magnetic forces twist and accelerate plasma into narrow, powerful jets. These jets can stretch thousands of light-years into space, acting like cosmic particle launchers. Particles trapped in AGN jets experience some of the most extreme environments imaginable. Magnetic fields of staggering intensity coil around them, forcing them to spiral along tightly wound paths. As they move, shockwaves within the jets propel them to energies that challenge our understanding of physics. These particles can be so energetic that they cross intergalactic distances with minimal loss, eventually striking Earth with forces that defy comparison to any earthly event. AGN thus rank among the strongest candidates for the very highest energy cosmic rays. Gamma-ray bursts, GRBs, represent another extraordinary candidate. These cataclysmic explosions originate from the collapse of massive stars into black holes or from the collision of neutron stars. GRBs release more energy in a few seconds than the Sun will emit during its entire lifetime. Their relativistic jets, traveling at nearly the speed of light, create environments where particle acceleration becomes violently efficient. Scientists believe that GRBs could produce particles with energies beyond even what AGN can generate. In GRBs, the combination of intense magnetic fields, rapid expansion, and shockwave interactions forms a perfect storm for particle acceleration. The jets rocket outward at relativistic speeds, sweeping up surrounding material and compressing it into turbulent shock zones. These zones rapidly energize particles, sending them flying across the cosmos. If even a tiny fraction of these particles escape, they could become the ultra-high-energy cosmic rays that occasionally strike Earth with bewildering power. Despite these leading hypotheses, the origins of cosmic rays remain partly mysterious. The winding paths that charged particles follow through galactic magnetic fields make it nearly impossible to pinpoint their exact sources. Instead of pointing directly back to their birthplace, cosmic rays arrive scrambled, their trajectories distorted by billions of years of twisting magnetic influence. Scientists therefore rely on statistical patterns, energy signatures, and elemental abundances to infer where they may have originated. To make matters more complex, cosmic rays come in multiple energy ranges, each likely tied to different types of astrophysical accelerators. Lower energy cosmic rays may originate from solar-wind interactions or mild stellar flares, whereas mid-energy rays likely come from supernova remnants. Extremely high-energy cosmic rays require far more powerful sources, such as AGN or GRBs. This layered distribution forms a cosmic hierarchy, where each energy domain hints at a different class of cosmic phenomena. The galaxy itself plays a role in confining and shaping cosmic rays. Its magnetic fields trap particles for millions of years, guiding them along spiral paths instead of letting them escape freely. During this confinement period, cosmic rays interact with interstellar gas and dust, undergoing spallation, where collisions break heavier nuclei into lighter elements. These fragmentation patterns help scientists determine how long cosmic rays have been traveling and what environments they've passed through. Supernova remnants remain the most locally influential sources. Their shockwaves fill the Milky Way with a steady stream of high-energy particles. Regions near star-forming galaxies, where massive stars are born and die frequently, can become cosmic ray hotspots. Our solar system, moving through the galaxy, occasionally passes through such regions, experiencing fluctuations in cosmic ray intensity that may subtly influence Earth's atmosphere and even biological evolution over geological timescales. While supernova remnants dominate galactic sources, AGN and GRBs are essential for explaining the rare ultra-high-energy particles that smash into Earth with unimaginable force. These particles, sometimes containing the kinetic energy of a thrown baseball, are so powerful that they spark immense particle showers upon striking the upper atmosphere. Their detection remains one of astrophysics' most compelling challenges, pushing scientists to investigate phenomena beyond current theoretical limits. Astronomers use an array of instruments, radio, X-ray, gamma-ray telescopes, and neutrino observatories to trace indirect signatures of cosmic ray acceleration. Supernova remnants emit synchrotron radiation when accelerated electrons spiral around magnetic fields. AGN glow brightly across the electromagnetic spectrum, revealing shock fronts where particles gain energy. GRBs produce flashes of high-energy photons that fade within seconds, but their afterglows expose regions where particle acceleration may have occurred. Even with these observational tools, the puzzle remains incomplete. Particles with the highest energies appear too powerful to be confined even by AGN jets, suggesting that we may still be missing some astrophysical mechanism. Some theories propose that exotic objects, magnetars, fast radio bursts, or even relics from the early universe could contribute to the cosmic ray population. These ideas expand the possibilities but also deepen the mystery. The Milky Way's structure influences cosmic ray propagation. Spiral arms contain clusters of supernova remnants, forming potential acceleration chains. As Earth orbits the galactic center, it passes through these arms over millions of years, potentially changing cosmic ray exposure. This cosmic geography suggests that Earth's radiation environment is not static but shifts over long periods, shaped by the galaxy's evolving architecture. Cosmic rays from AGN and GRBs often originate millions or billions of light-years away. Their ability to reach Earth intact demonstrates the remarkable resilience of high-energy particles. Along their journey, they may encounter intergalactic magnetic fields, cosmic microwave background photons, and patches of dark matter. Each encounter leaves subtle imprints on the particle's energy spectrum, allowing scientists to piece together intergalactic conditions much as archaeologists reconstruct ancient civilizations from scattered artifacts. One challenge in identifying cosmic ray origins lies in distinguishing source-generated particles from secondary particles produced during travel. Interactions with interstellar gas can modify the composition of cosmic rays over time. Scientists must carefully analyze these alterations to infer the particle's original nature. In this way, cosmic ray research becomes a kind of cosmic chemistry, tracking isotopes and elemental signatures across millions of light-years. Supernova remnants remain strong candidates because their energy output and frequency match the observed cosmic ray flux. Each supernova injects enormous amounts of kinetic energy into surrounding space, and with millions of such events over the galaxy's history, they collectively provide a steady stream of accelerated particles. The consistency of this process supports the idea that supernova shocks dominate the production of galactic cosmic rays. AGN, however, excel at explaining cosmic rays with energies beyond the so-called knee in the spectrum. The monstrous gravitational power of supermassive black holes creates conditions where particle acceleration becomes nearly limitless. Jets launched by AGN pierce intergalactic space with energies that travel unchanged for unimaginable distances. These jets form some of the most visually striking structures in the universe, and studying them provides clues to the behavior of cosmic rays at the highest energies. Gamma-ray bursts remain more mysterious due to their rarity and short duration. However, their immense energy release in such brief intervals suggests they may be indispensable sources for ultra-high-energy cosmic rays. Each burst unleashes a torrent of radiation and particle acceleration that could contribute significantly to the cosmic ray population, especially given their ability to generate extreme shock conditions. Ultimately, the origins of cosmic rays likely lie not in one source but in many. The cosmos is diverse, filled with explosive events and gravitational monsters that push matter to extremes. Cosmic rays represent the combined output of these cosmic engines, a fusion of supernova shockwaves, black hole jets, and relativistic explosions. Each particle that reaches Earth carries a faint echo of these cataclysmic events, allowing scientists to piece together a story that spans galaxies and epochs. Understanding where cosmic rays come from means understanding how the universe energizes matter, how magnetic fields shape cosmic history, and how explosive events sculpt the cosmos across billions of years. Each source, supernova remnants, AGN, and GRBs, contributes a unique chapter to this ongoing story. And as detectors become more advanced, scientists move closer to tracing these ancient, high-speed messengers back to the cosmic furnaces that forged them. The mystery of ultra-high-energy cosmic rays, UHECR's particles so powerful we can barely comprehend their origin. These extraordinary particles represent the extreme edge of the cosmic ray spectrum, carrying energies so vast that one of them can match the kinetic energy of a Major League Baseball thrown by a professional player. To imagine a subatomic particle holding that much power is almost beyond human intuition, yet detectors on Earth have confirmed their existence. They strike our atmosphere with such ferocity that they generate colossal particle showers spreading across kilometers, leaving scientists stunned and eager to understand their birthplace. UHECRs defy conventional astrophysical explanations. The known accelerators, supernova remnants, pulsars, AGN jets, can create extremely energetic particles, but UHECRs surpass those expectations by orders of magnitude. The mechanisms required to accelerate a proton or nucleus to these energies would demand magnetic fields and astrophysical environments far more extreme than typical cosmic explosions. Their presence suggests either unknown astrophysical engines or new physics that challenges current theories about particle behavior and cosmic forces. One of the greatest puzzles about UHECRs is how they maintain their energy across vast cosmic distances. As they travel through intergalactic space, they encounter background photons, magnetic fields, and diffuse gas. Normally, these interactions would sap their energy gradually. Yet the highest energy cosmic rays seem to arrive at Earth relatively intact, implying either that they originate surprisingly nearby or that they were accelerated so powerfully that even energy losses over millions of light-years barely dent their momentum. This paradox fuels ongoing debates among astrophysicists. These particles are so rare that large observatories detect only a handful per year. Their scarcity makes each detection an event of scientific excitement, requiring arrays of detectors spread across large regions of land. The Pierre Auger Observatory in Argentina and the Telescope Array in Utah are two of the leading facilities tracking UHECRs. Using thousands of sensors, they monitor atmospheric particle showers with extraordinary precision. Each detection becomes a clue, a tiny fragment of data guiding scientists toward understanding the colossal processes shaping the universe's most energetic events. When a UHER hits Earth's atmosphere, it triggers an air shower unlike any produced by lower-energy cosmic rays. The incoming particle collides with atmospheric nuclei, releasing a burst of secondary particles that cascade downward at nearly light speed. The resulting shower spreads out over huge distances, allowing ground detectors to measure its footprint. The scale of these showers signals the unimaginable energies involved, highlighting just how different UHECRs are from ordinary cosmic rays that strike Earth millions of times per second. The composition of UHECRs adds further mystery. Some appear to be protons, while others are heavy atomic nuclei like iron. Heavy nuclei complicate the picture because they are more easily disrupted during intergalactic travel. If these particles truly originate millions of light-years away, they should fragment along the way. Yet observations show intact nuclei, arriving at Earth with extraordinary energies. This contradiction suggests that either they originate relatively nearby or they travel through regions of space unusually empty or weak in interactions. Scientists once believed UHECRs would exhibit a strict energy limit imposed by the Greisen-Ersatzapin-Kuzmin (GZK) cutoff, caused by interactions with the cosmic microwave background. According to this prediction, cosmic rays above a certain energy should not travel far without losing significant momentum. However, detections repeatedly approach or exceed this cutoff, hinting that the universe may contain pockets or routes where energy loss is minimized. These anomalies have pushed researchers to reconsider long-held assumptions about cosmic distances and particle propagation. The possibility exists that UHECRs originate from rare, extreme astrophysical events. Some theoretical models propose that newly formed magnetars, neutron stars with magnetic fields trillions of times stronger than Earth's, could accelerate particles to ultra-high energies. Others suggest that galaxy clusters with turbulent magnetic fields might trap and energize particles over millions of years. While these ideas remain speculative, they represent serious attempts to identify mechanisms capable of producing energy levels beyond what AGN jets or supernova remnants can deliver. Gamma-ray bursts also remain strong contenders. Their relativistic jets, containing unimaginable amounts of energy, could theoretically accelerate particles to UHER levels in very short bursts. If Earth coincidentally lies within the narrow beam of such a burst, some of these particles might reach us after traveling through intergalactic space. However, the rarity of GRBs makes them unlikely to account for all observed UHECRs, unless their acceleration mechanisms are far more efficient than current models assume. Active galactic nuclei remain another leading candidate. AGN jets, driven by supermassive black holes, create environments dense with magnetic fields and shock fronts. These jets can extend for hundreds of thousands of light-years, acting like gigantic particle accelerators. Some models suggest that the shear between different layers of a jet could energize particles to UHER levels. However, whether AGN can genuinely reach those extreme energy thresholds remains an open question, particularly given observational limitations. A more exotic possibility is that UHECRs originate from processes outside standard astrophysics, perhaps from phenomena related to dark matter or relic particles from the early universe. Some theoretical models propose that the decay of supermassive particles left over from the Big Bang could produce UHECRs as byproducts. These hypothetical particles, sometimes called top-down sources, would release immense energy upon decaying. If true, UHECRs could be clues to understanding physics beyond the standard model. Another intriguing idea is that cosmic strings, hypothetical one-dimensional defects in spacetime, could generate bursts of energy when they snap or interact. These extreme events might produce particles with unimaginable energies, creating UHECRs detectable on Earth. While cosmic strings have not been observed, their theoretical implications attract physicists interested in understanding early universe physics. UHECRs could potentially offer indirect evidence for such exotic structures. UHECRs also offer a rare opportunity to probe intergalactic magnetic fields. These fields are incredibly weak and difficult to measure directly. Yet the paths that UHECRs take, twisted and bent by magnetic interactions, hold clues to their structure. By examining the slight clustering or directional scattering of incoming particles, scientists attempt to reconstruct the magnetic landscape of intergalactic space. Each UHER becomes a tracer particle revealing invisible structures across cosmic distances. Despite decades of study, no single source class conclusively explains all observed UHECRs. Their diversity in energy, composition, and arrival patterns suggests that multiple origins are likely. This complexity hints at a universe filled with diverse and powerful engines capable of shaping matter at the deepest level. UHECRs force scientists to expand the boundaries of imagination and consider extreme physical environments beyond anything directly observable. The difficulty of pinpointing UHER origins stems from the way cosmic magnetic fields distort their trajectories. A proton or nucleus traveling billions of light-years may encounter countless magnetic fluctuations, erasing any directional information. By the time the particle reaches Earth, it no longer points back to its source. This makes UHER research one of the most frustrating and fascinating detective challenges in modern astrophysics, requiring creative analysis and increasingly sophisticated models. UHECRs also interact with Earth's atmosphere in ways that push the limits of particle physics. The showers they produce contain particles at energies far higher than those generated at the Large Hadron Collider. This means scientists can use cosmic rays as a natural high-energy laboratory, observing interactions that remain inaccessible to human-made experiments. These observations can reveal subtle deviations from expected physics, potentially pointing to new phenomena or unknown particles. One striking observation is the clustering of some UHER detections toward specific regions of the sky. While these clusters are faint and not yet definitive, they hint at possible source regions, such as nearby AGN or galaxy clusters. Continued monitoring may eventually reveal consistent directional patterns, allowing scientists to connect UHECRs with specific astrophysical objects. Such a breakthrough would revolutionize our understanding of cosmic acceleration processes. Even the energy spectrum of UHECRs raises questions. The gradual steepening of the spectrum beyond the knee and ankle regions reflects transitions between different acceleration sources. But at the highest energies, the spectrum becomes sparse and unpredictable. This irregularity suggests that UHECRs originate from rare and powerful events rather than steady astrophysical processes, reinforcing the idea that their sources may be exceptionally uncommon or exotic. Understanding UHECRs has implications far beyond astrophysics. Their interactions help shape atmospheric chemistry, influence particle backgrounds for experiments, and inform our understanding of radiation environments in space. For future human exploration of the solar system, predicting UHER fluxes becomes essential for ensuring astronaut safety, especially for missions beyond Earth's magnetosphere where protective shielding is minimal. The incredible energies of UHECRs push theoretical models to their limits. The Lorentz factors involved, measures of relativistic transformation, become so extreme that they challenge assumptions about particle stability, shock acceleration, and magnetic confinement. Each new detection tests these limits, forcing theorists to reconsider how matter behaves under the most intense conditions nature can produce. The distribution of UHECRs across the sky also hints at large-scale cosmic structure. Slight anisotropies in their arrival directions correlate loosely with the distribution of galaxies within about 200 million light-years. This suggests that at least some UHECRs originate from relatively nearby extragalactic sources. The challenge remains distinguishing whether these correlations reflect true source directions or magnetic steering effects. As detection technology improves, scientists hope to capture larger datasets, enabling more precise conclusions. Next-generation observatories will use radio detection, fluorescence telescopes, and expanded surface arrays to measure UHECRs with unprecedented accuracy. These instruments aim to clarify their composition, energy distribution, and possible directional clustering, gradually unraveling the cosmic riddles that UHECRs embody. Ultimately, UHECRs remind us of how limited our understanding of the universe still is. These particles push the boundaries of physics, challenging assumptions about energy limits, acceleration processes, and cosmic structures. Each one is a messenger from an environment so extreme that it transcends ordinary astrophysical processes. Their presence hints at forces, objects, or events that we barely comprehend, pushing science toward deeper and more profound questions about the nature of reality itself. The long, winding path. How magnetic fields across galaxies and intergalactic space bend and deflect cosmic rays. When a cosmic ray is first launched from its birthplace, perhaps the violent shock front of a supernova or the blazing jets of an active galactic nucleus, it does not travel in a clean, laser-straight line toward Earth. Instead, it enters a cosmic labyrinth made of magnetic forces stretching across the universe. These magnetic fields, though incredibly weak compared to anything generated on Earth, are vast and persistent, guiding, curving, twisting, and sometimes scattering these particles so thoroughly that by the time they finally arrive, all clues pointing to their original direction may be scrambled beyond recognition. Cosmic rays behave like charged bullets fired into a maze of invisible wires. Every time they cross a magnetic field line, the particle's path bends according to its charge, speed, and the strength of the field. Even a minuscule deviation repeated over billions of miles becomes enormously significant, turning what could have been a direct journey into a dizzying voyage filled with detours. This bending is not simply a small correction, it can dramatically reshape the trajectory, converting a simple path into a spiraling dance that stretches across light-years of magnetic turbulence. The Milky Way itself is wrapped in a vast, tangled, magnetic web that acts like both a barrier and a guide. Cosmic rays entering our galaxy must weave through this structure, and because the field's strength varies from region to region, a particle may speed through one pocket before encountering another where it is pulled into a looping turn. These interactions can delay the particle's arrival by thousands or even millions of years compared to its expected straight-line travel time, meaning the cosmic rays hitting us today may have been launched long before humanity existed. Even before cosmic rays enter a galaxy like ours, they face the even broader magnetic fields of intergalactic space. Though weaker, these fields can extend over millions of light-years, shaping the motion of particles long before they meet the magnetic environment of any individual galaxy. These intergalactic fields are often patchy, sometimes behaving like fluid streams that gently push cosmic rays off course, other times swirling around galaxy clusters in chaotic, turbulent patterns that scatter particles in unpredictable directions. As cosmic rays travel, each encounter with a magnetic field bends their paths into arcs determined by the particle's rigidity. High-energy cosmic rays with enormous momentum bend less than low-energy ones, giving them straighter trajectories. Yet even the most energetic particles, with energies far beyond anything Earth can produce, still feel the influence of these faint cosmic magnetic fields, their paths curving ever so slightly, altering the angle at which they ultimately collide with our planet's atmosphere. The result of these countless interactions is that when scientists detect a cosmic ray on Earth, its arrival direction is not necessarily a trustworthy pointer back to its birthplace. The universe has effectively scrambled the trails, leaving researchers with a puzzle: how to reconstruct the origin of a particle that has wandered through an entire cosmic forest of invisible magnetic branches. This uncertainty is one of the reasons cosmic rays remain one of the most mysterious messengers in astrophysics, as their true sources are notoriously difficult to pinpoint. In some regions of space, magnetic fields cluster into filaments, especially around galaxy clusters, forming something like a network of cosmic highways and detours. A cosmic ray passing through such structures may experience a gentle drift in one region, a sharp twist in another, and a whirling delay in yet another. By the end of its journey, the particle may have traveled a path many times longer than the direct distance between its source and Earth, accumulating countless directional changes like a traveler wandering through an unfamiliar, winding city. Even within our own galaxy, the magnetic field is not a uniform blanket but a complex system featuring spiral arms, loops, bubbles, and turbulent eddies. Cosmic rays moving through these structures encounter varying intensities and orientations of magnetic fields, making their path through the Milky Way as chaotic as their intergalactic journey. These layers of magnetic influence stack on top of each other, each adding new complications to the trajectory of the particle. Because cosmic rays are charged, their movement through magnetic fields follows predictable equations of motion at a fundamental level. Yet the sheer scale and complexity of cosmic magnetic structures make exact calculation nearly impossible. Instead, researchers must rely on statistical modeling, simulations, and indirect clues gleaned from the distribution and energy spectrum of the particles. This complexity is why tracing a cosmic ray to its birthplace remains so challenging. For ultra-high-energy cosmic rays, the bending is reduced but not eliminated. Their enormous rigidity allows them to plow through magnetic fields with less deviation, but even then, the cumulative effect over millions of light-years can alter their path enough to obscure their origin. These particles may arrive with a direction that only vaguely hints at where they emerged, providing scientists with a blurred map rather than a clear pointer. The interplay between cosmic rays and magnetic fields becomes even more fascinating when considering that cosmic rays themselves may help shape magnetic structures. As charged particles stream through space, they can interact with plasma, generating instabilities and contributing to turbulence. In this way, cosmic rays both respond to and subtly influence the magnetic environment through which they travel, creating a feedback loop that spans cosmic distances. In galaxy clusters, magnetic fields can reach greater strength and display higher levels of turbulence. Cosmic rays entering such clusters may face intense scattering, bouncing between magnetic pockets like pinballs in a giant arcade. This turbulent scattering can completely destroy the particle's initial direction, effectively making its eventual arrival at Earth a matter of probability rather than a traceable path. When cosmic rays approach the Milky Way, they encounter the heliosphere, the protective magnetic bubble inflated around our solar system by the solar wind. This region adds another layer of deflection, especially for lower energy particles, which are more sensitive to changes in magnetic intensity. The Sun's activity level can strengthen or weaken the heliosphere's magnetic influence, meaning the Earth's cosmic ray flux subtly fluctuates with solar cycles. Even after navigating the vast cosmic magnetic fields and the heliosphere, cosmic rays still face Earth's own geomagnetic field. This field filters incoming particles based on their energy and angle of arrival, bending the paths of lower-energy cosmic rays and preventing many from hitting the atmosphere. Only the highest-energy particles can punch straight through with minimal deflection, highlighting yet another barrier that modifies their trajectories. The cumulative effect of all these layers, intergalactic magnetic fields, galactic magnetic networks, solar magnetic shielding, and Earth's magnetic defenses, creates a labyrinth that cosmic rays must navigate. Each layer introduces new twists, preventing scientists from easily using arrival directions as maps back to the source. As a result, cosmic ray astronomy is uniquely challenging compared to other forms of astrophysical investigation. Although scientists cannot easily trace the exact path of each cosmic ray, they can sometimes identify correlations. For example, clusters of high-energy cosmic rays arriving from similar regions of the sky hint at potential source locations. These statistical patterns help researchers narrow down candidate sources, but they still must work against the constant scrambling caused by magnetic fields. One of the most mind-bending aspects of cosmic ray deflection is the possibility that a cosmic ray originating from a relatively nearby galaxy could have taken a wildly longer path due to magnetic twisting. In extreme cases, a particle from a source only a few million light-years away may have traveled a path so convoluted that its total journey spanned hundreds of millions of light-years in effective length. To visualize this wandering path, imagine tracing a long, tangled string thrown across vast cosmic structures. Every knot, twist, and loop represents a deflection caused by magnetic fields. Now imagine that string stretching across distances so immense that even light, the fastest thing in the universe, would need millions of years to traverse them. This is the true complexity of a cosmic ray's journey. Scientists study the bending of cosmic rays not only to understand the particles themselves but also to map magnetic fields across the universe. Since these fields are nearly invisible, cosmic rays effectively act as probes, their deflected paths carrying clues about the strength and distribution of magnetic structures they encountered. In this way, cosmic rays serve as messengers not only of energetic astrophysical events but also of the hidden architecture of the cosmos. At the same time, cosmic magnetic fields act as a natural shield for life. By deflecting many energetic particles, they prevent Earth from being constantly bombarded by high-energy cosmic radiation. This protection highlights the dual nature of magnetic fields. They complicate cosmic ray research but also make life on Earth possible, balancing scientific difficulty with biological safety. Ironically, the very thing that makes cosmic rays valuable as messengers, their ability to travel across cosmic distances, also makes them incredibly difficult to interpret. Their winding journey through magnetic fields turns them into distorted clues, forcing scientists to decipher their origins through indirect means. This makes cosmic ray astrophysics more like detective work than simple measurement. Despite these challenges, the scientific community continues to develop new techniques, using vast arrays of detectors and advanced simulations to untangle the cosmic ray mystery. Projects like the Pierre-Auger Observatory and the Telescope Array are designed to capture enormous numbers of high-energy particles, providing the data needed to overcome the confusion introduced by magnetic fields. Each cosmic ray that reaches Earth carries the imprint of its long, winding path, a subtle record of the magnetic structures it encountered. By collecting vast amounts of data and comparing arrival patterns, scientists can gradually peel back the layers of cosmic complexity, revealing the underlying structures and perhaps even identifying the ultimate origins of these powerful particles. In the end, the bending and twisting of cosmic rays through magnetic fields is not just an obstacle, it is a story written across the universe. These particles do not travel in straight lines because the cosmos itself is not a simple, empty void. It is a dynamic, magnetized, turbulent environment, and every cosmic ray that reaches us carries the memory of that environment etched into its journey. How we detect them, from ground-based observatories like Pierre-Auger to space-based detectors like AMS-02 on the ISS. The detection of cosmic rays is a scientific challenge unlike most others because these particles do not arrive gently or intact. Instead, when they hit Earth's atmosphere, they smash into molecules at incredible energies, creating cascading showers of secondary particles that spread out over large areas. To detect them, scientists must monitor vast stretches of land with sensitive instruments capable of catching these fleeting signals. Observatories like the Pierre-Auger facility in Argentina have been designed to capture these particle showers by spreading out thousands of detectors across a landscape so wide that only extremely energetic events can activate multiple sensors at once, revealing the direction and energy of the incoming cosmic ray. Unlike observatories that rely on telescopes and lenses, cosmic ray detectors depend on what happens in the atmosphere. When an ultra-energetic cosmic ray collides with an air molecule, it triggers a chain reaction that produces electrons, muons, photons, and other short-lived particles. These secondary particles travel downward like a rainstorm of invisible sparks. Ground detectors measure the timing and strength of these particles to reconstruct the original cosmic ray. Because these particle showers spread across several square kilometers, researchers need long-term monitoring, precise timing arrays, and powerful computers to separate meaningful events from background noise. The Pierre Auger Observatory uses water Cherenkov detectors, large tanks filled with pure water. When secondary particles from a cosmic ray shower pass through the water, they move faster than light can travel in that medium, creating a faint blue glow known as Cherenkov radiation. Sensitive photomultiplier tubes inside the tanks capture this glow, converting it into electrical signals. The timing of these signals across thousands of tanks allows scientists to map the shape and angle of the incoming shower, revealing how powerful the original cosmic ray must have been. In addition to the water tanks, Auger also employs fluorescence telescopes that watch the night sky for faint ultraviolet flashes produced by nitrogen molecules excited by the particle cascades. These flashes only occur during clear, dark nights, but when they do, they allow scientists to directly view the shower's development through the atmosphere. By combining data from both sources, surface detectors and atmospheric fluorescence, the observatory gains a fuller picture of cosmic rays and their energies. Another major facility, the Telescope Array in Utah, uses a similar approach but covers the northern hemisphere. Triangulating results from both hemispheres allows scientists to compare patterns and see if cosmic rays arrive preferentially from certain regions of the sky. Because cosmic ray arrival directions may hold subtle clues about their origins, the collaboration between these large observatories is essential, helping to determine whether events detected in the south correlate with those observed in the north. Even though ground-based observatories capture the effects of cosmic rays after they collide with the atmosphere, space-based detectors take a more direct approach by catching cosmic rays before they interact with anything. Instruments like the Alpha Magnetic Spectrometer, AMS-02, mounted on the International Space Station, drift above the disturbance of Earth's atmosphere. This gives them the ability to measure incoming particles directly, identifying their charge, energy, and mass with far greater precision. AMS-02 uses strong magnetic fields to bend the paths of charged particles, allowing scientists to determine the sign and magnitude of their charge. By analyzing how much a particle bends, along with its velocity and energy deposition in the detector modules, AMS-02 can distinguish between protons, electrons, positrons, and various atomic nuclei. This level of detail helps reveal the composition of cosmic rays and provides important clues about where they may originate. Because AMS-02 orbits Earth, it continuously sweeps through different regions of space, collecting an enormous sample of particles. Over its mission lifetime, it has accumulated data on billions of cosmic rays. This vast dataset allows researchers to identify subtle patterns and anomalies that might be impossible to detect using only ground-based observatories, making AMS-02 one of the most important tools in modern cosmic ray physics. One of the advantages of space-based detectors is the absence of atmospheric interference. On Earth, many particles in a cosmic ray shower may go undetected, decay before they reach the surface, or be lost in background radiation. But in space, even low-energy particles can be measured with high precision. This makes space-based detectors ideal for studying cosmic rays originating within our galaxy, including antimatter signatures that might hint at dark matter interactions. Scientists also use balloon-borne detectors, which float high in the stratosphere, above most of the atmosphere but below the complexities of orbit. These balloon missions carry sophisticated instruments capable of directly measuring cosmic rays for days or even weeks. Because they fly much closer to Earth than satellites, researchers can retrieve the equipment after flight, upgrade components, and relaunch them for future observations, making balloon missions an invaluable platform for testing new cosmic ray detection technologies. Balloon missions like CREAM, cosmic ray energetics and mass, have provided crucial measurements of cosmic ray nuclei, helping scientists understand how their energy spectra change over time and what this reveals about cosmic acceleration mechanisms. These missions bridge the gap between Earth-based detectors and full-space observatories, offering flexibility and precision without the extreme cost of satellite launches. In addition to massive observatories, smaller ground-based detectors scattered across universities and research centers contribute to the global detection network. Students, teachers, and physicists use simple scintillator panels that light up when struck by charged particles from cosmic ray showers. These modest detectors allow widespread, coordinated monitoring, turning the entire planet into a giant cosmic ray sensor. This collaborative approach helps validate major findings and gives more detailed temporal tracking of cosmic ray flux. Scintillator detectors work by converting particle energy into brief flashes of light. Photodetectors then translate these flashes into digital signals. When several such detectors are arranged in a network and synchronized by GPS timing, they can detect particle showers spreading across large distances. This method contributes to educational outreach and citizen science while still generating real scientific data. Another method of detection involves radio waves. When cosmic ray showers propagate through the atmosphere, they generate faint radio emissions due to the motion of charged particles in Earth's magnetic field. Experiments like LOFAR in Europe use large arrays of radio antennas to pick up these signals, providing an entirely different perspective on the showers. Because radio detection works day and night and even in cloudy conditions, it complements facilities that rely on optical signals. Researchers are also exploring the use of radar reflections to detect cosmic ray showers. When a shower ionizes a column of air, it temporarily reflects radio waves much like a meteor trail. Although this method is still in development, the potential to detect cosmic rays using radar could revolutionize high-energy astrophysics by enabling wide-area monitoring with relatively low-cost equipment. Another innovative technique uses gamma-ray observatories to detect the indirect signatures of cosmic rays interacting with interstellar gas. When cosmic rays collide with matter in the galaxy, they produce gamma rays that can be detected by space telescopes like Fermi-LAT. While this method does not measure the cosmic rays directly, it reveals their distribution across the galaxy, offering valuable information about where they propagate and how they interact with the interstellar medium. Even underground detectors play a role in cosmic ray science. Facilities built deep beneath mountains or in abandoned mines primarily search for dark matter or neutrinos, but they also measure muons, secondary particles created by cosmic ray showers. These muons can travel far underground, allowing detectors to track their arrival patterns and energies. This contributes an additional layer of data that helps refine models of cosmic ray propagation. The challenge for scientists is not only to detect cosmic rays but to accurately reconstruct their properties. Every instrument, whether it measures Cherenkov light, fluorescence flashes, magnetic bending, or radio signatures, captures a different piece of the cosmic puzzle. By combining all these techniques, researchers form a multi-layered observational framework that improves accuracy and reduces uncertainties in cosmic ray analysis. Advanced computer simulations also play a critical role. By modeling how cosmic ray showers develop through the atmosphere and how detectors respond to them, scientists can interpret real-world data more accurately. These simulations require enormous computational power and are constantly refined as new measurements become available. The synergy between simulation and observation is essential, given the chaotic nature of atmospheric particle cascades. Monitoring cosmic rays over long periods reveals how their flux changes with solar cycles. As the sun's magnetic activity rises and falls, it alters the number of low and mid-energy cosmic rays that reach Earth. Detectors around the world track these variations, helping scientists understand solar modulation and its influence on space weather. Ground-based neutron monitors play a key role in this research, offering decades-long datasets that show how cosmic ray intensity fluctuates across solar cycles. Cosmic ray detection is not limited to Earth-based science, it is also essential for astronaut safety. Instruments aboard spacecraft measure cosmic radiation levels to protect astronauts from harmful exposure. These detectors provide real-time monitoring and contribute to mission planning, especially for deep space missions where cosmic radiation becomes a significant hazard. The same technologies used for cosmic ray science help ensure the safety of human explorers beyond Earth. The combination of ground-based arrays, space-based observatories, balloon missions, and underground detectors provides a comprehensive and layered strategy for studying cosmic rays. Each method offers strengths that compensate for the limitations of others. Together, they allow scientists to build a clearer picture of the energies, compositions, and origins of cosmic rays, even when the particles themselves refuse to travel in straight lines or reveal their paths easily. Many of the instruments used today represent decades of innovation, refinement, and international collaboration. Countries around the world contribute to these massive projects, sharing data and building unified networks that monitor the planet's entire cosmic ray environment. This global cooperation reflects the universal nature of cosmic rays themselves, particles that cross borders, galaxies, and epochs without hesitation. As detection technology continues to evolve, new observatories are being designed to push the limits of sensitivity and precision. Proposed detectors on the Moon or in deep space could one day record cosmic rays with unprecedented clarity, reducing the interference caused by Earth's atmosphere and magnetic field. Such advances may finally help scientists pinpoint the true sources of the highest energy particles in the universe. Despite all challenges, the ability to detect cosmic rays across multiple environments, from the deepest underground labs to the edge of space, stands as one of the greatest achievements of modern astrophysics. Each particle captured represents a fragment of a cosmic story billions of years in the making, and with every new detection, humanity moves one step closer to understanding the violent, mysterious universe that created them. What we learn from them, clues about the universe's most violent events, dark matter searches, and even the history of our solar system. When we study cosmic rays, we are not simply measuring high-energy particles, we are collecting fragments of ancient cosmic stories written in energy, composition, and arrival patterns. Each particle carries with it the imprint of the environment where it was born, shock waves from exploding stars, jets from supermassive black holes, or other cataclysmic events so powerful that they reshape galaxies. By analyzing the energies and types of particles in cosmic ray flux, scientists can piece together the fingerprints of these violent cosmic processes, revealing the hidden mechanisms behind the most extreme accelerators in the universe. Cosmic rays tell us that supernovae are not gentle cosmic winds but explosive factories of energy capable of hurling particles at nearly light speed. Their energy spectra suggest the presence of shock acceleration, a process where particles gain speed by bouncing back and forth across supernova shock fronts. These observations confirm theoretical predictions that supernova remnants are among the primary sources of galactic cosmic rays. By matching specific isotopic abundances detected in cosmic rays with those predicted by nucleosynthesis models, scientists can even determine the types of stars that exploded and how those explosions contributed material to our galaxy. One of the most surprising lessons cosmic rays offer is that some energies are far too great to be produced by ordinary supernovae. Ultra-high-energy cosmic rays exceed 10 to the power of 20 electron volts, suggesting they were launched by cosmic engines far more powerful than typical stellar explosions. These energies provide indirect evidence of exotic environments, the turbulent hearts of active galactic nuclei, the knife-like jets fired from accretion disks around black holes, or gamma-ray bursts capable of outshining entire galaxies. Without cosmic rays, we would have no direct way to probe these extraordinary accelerators. Cosmic rays also act as probes that travel through the cosmic web, sampling magnetic fields, gas clouds, and interstellar turbulence. Their energy losses, deflections, and interactions reveal the structure of the universe on scales far beyond what telescopes can see. In a sense, cosmic rays behave like messengers that have wandered through galactic wilderness, returning with stories about the density of intergalactic matter, the strength of magnetic fields, and the hidden architecture of the cosmic environment. When cosmic rays collide with interstellar gas, they create secondary particles and gamma rays. These interactions help astronomers map the distribution of interstellar hydrogen and track regions where star formation has recently occurred. Thus, cosmic rays serve not only as clues to the violent events that produced them but also as traces of galactic ecology, allowing scientists to reconstruct how energy flows through the Milky Way and how regions of space evolve over millions of years. Cosmic rays even provide insights into the early history of our solar system. Some particles contain isotopes that could only have been produced in the first few million years after the Sun formed. By comparing these isotopes with those found in meteorites and planetary samples, researchers can reconstruct ancient cosmic bombardment rates, solar activity levels, and the early conditions that shaped the planets. This helps explain why Earth developed differently than Mars or the Moon in terms of atmospheric evolution and surface chemistry. Because cosmic rays arrive with a wide range of energies, they offer a way to study astrophysical processes across different scales. Low-energy cosmic rays trace more common galactic processes, while mid-energy ones hint at star-forming regions and pulsars. The highest energy particles, however, point toward the universe's most extreme accelerators. Understanding why different energies appear in different quantities allows scientists to reverse engineer the physical environments where they were created. One of the most exciting scientific frontiers involving cosmic rays is the search for hints of dark matter. Certain cosmic ray particles, such as excess positrons or unusual antiproton ratios, may originate from dark matter annihilation or decay. If dark matter particles collide and annihilate, they could release detectable cosmic ray signatures. Instruments like AMS-02 and DAMP have captured intriguing anomalies that might indicate dark matter interactions, although alternative astrophysical explanations remain possible. Cosmic rays may therefore hold the key to uncovering one of the universe's deepest mysteries. Cosmic rays also reveal something about the fundamental symmetry of matter and antimatter. While ordinary matter dominates the universe, cosmic ray detectors occasionally capture antimatter nuclei, such as antihelium or anticarbon. These rare events could signal regions of the universe where antimatter persisted after the Big Bang, or they could be produced in exotic events like dark matter annihilations. Discovering large amounts of antimatter cosmic rays would revolutionize our understanding of cosmology, potentially forcing scientists to rethink the earliest moments of the universe. Cosmic rays indirectly show that the Milky Way is an active and dynamic place rather than a quiet cosmic backwater. Their distribution suggests continuous acceleration by supernova remnants, star-forming regions, and large-scale magnetic turbulence. This implies that our galaxy is constantly reshaping its energy balance, recycling material through stellar explosions and dispersing it through interstellar space. Cosmic rays offer a record of this ongoing activity etched into their composition and energy. Studies of cosmic rays also show how galaxies evolve over cosmic time. As galaxies grow, merge, and undergo starbursts, their cosmic ray output changes accordingly. By observing cosmic ray interactions in distant galaxies via gamma-ray emissions, astronomers can infer the history of star formation and explosive events that shaped those galaxies billions of years ago. Cosmic rays thus provide a timeline of galactic evolution encoded in high-energy interactions. Cosmic ray isotopes reveal how long these particles have been traveling through the galaxy. Certain radioactive isotopes decay over predictable timescales, acting like cosmic clocks. By measuring their abundance, scientists can estimate how long cosmic rays have been wandering through interstellar space, sometimes millions of years. These cosmic clocks allow researchers to determine how quickly cosmic rays diffuse through the galaxy and how far they travel before escaping into intergalactic space. Another remarkable insight from cosmic rays is that particles can achieve energies far beyond what human-made accelerators can produce. Even the Large Hadron Collider cannot reach energies comparable to the highest energy cosmic rays. This means nature has built accelerators vastly superior to anything humans have engineered, and cosmic rays offer a way to study physics under conditions that cannot be replicated on Earth. They provide a natural laboratory for testing theories about particle interactions at extreme energies. Cosmic rays also interact with Earth's atmosphere in ways that allow us to study atmospheric chemistry and climate processes. They contribute to the ionization of the upper atmosphere, which may influence cloud formation and atmospheric electricity. While the exact role of cosmic rays in climate is still debated, studying their effects helps refine our understanding of Earth's atmospheric dynamics. The interaction of cosmic rays with lunar soil provides a long-term record of cosmic radiation. Because the Moon lacks a protective atmosphere and magnetic field, cosmic rays leave signatures in the regolith that accumulate over billions of years. By analyzing these isotopic signatures, scientists can reconstruct ancient cosmic ray flux and uncover how the Sun and galaxy behaved long before humans existed. Lunar samples thus serve as cosmic archives preserved in dust and rock. Cosmic rays also shape the chemistry of interstellar clouds, influencing how molecules form in the coldest regions of space. They trigger reactions that produce complex organic molecules, precursors to life, within dense molecular clouds. Understanding cosmic ray ionization rates helps scientists model star formation and the creation of organic compounds that may eventually seed new planetary systems. The study of cosmic rays has revealed the existence of vast magnetic structures around galaxies. When cosmic rays interact with these fields, their trajectories reveal the field's shapes and strengths. Without cosmic rays, these magnetic structures would be nearly invisible. Their discovery has helped refine models of galaxy formation, showing that magnetic fields play a significant role in shaping galactic evolution. Observations of cosmic ray anisotropies, small variations in the arrival direction of particles, suggest that cosmic rays are not distributed uniformly across the sky. These tiny directional biases hint at nearby sources, local magnetic irregularities, or past explosions that still influence the flow of cosmic particles. Each anisotropy serves as a clue pointing toward dynamic activity in our galactic neighborhood. The presence of heavy nuclei in cosmic rays shows that they originate from environments where elements are forged in extreme conditions. By studying these heavy elements, scientists can confirm theories of stellar nucleosynthesis, supporting the idea that many elements in our bodies were created in ancient stars and scattered across the galaxy through explosive events. Cosmic rays thus help complete the story of where matter comes from. Cosmic rays even help constrain models of interstellar dust distribution. When particles travel through dust-rich regions, they lose energy or undergo collisions that alter their composition. Analyzing these changes allows astronomers to map the density and composition of dust clouds scattered throughout the Milky Way. This in turn helps refine models of star formation and galactic structure. One of the more unexpected insights from cosmic rays involves the heliosphere, the bubble carved out by the solar wind around our solar system. As cosmic rays enter the heliosphere, they experience modulation by solar magnetic activity. By studying how cosmic ray flux changes over time, scientists can reconstruct past solar activity levels, providing valuable data for understanding the Sun's long-term behavior. Cosmic rays also reveal information about the intergalactic medium. High-energy particles lose energy through interactions with background photons, such as the cosmic microwave background. These energy losses help confirm predictions about the density and temperature of intergalactic space, offering another piece of evidence supporting the Big Bang model and the expansion of the universe. In some cases, cosmic ray interactions produce neutrinos, elusive particles that barely interact with matter. Observatories like IceCube detect these neutrinos, allowing scientists to trace them back to their sources. Cosmic ray-induced neutrinos act as clean messengers because they travel in straight lines, unlike charged cosmic rays. This gives researchers an alternative way to pinpoint the violent astrophysical events that first launched the cosmic rays. By studying cosmic rays, physicists gain insights into fundamental particle interactions, nuclear processes, and high-energy physics. These particles provide natural experiments that push theoretical models to their limits. When cosmic rays break known patterns, they prompt scientists to search for new physics or revise existing theories. This interplay makes cosmic ray research a fertile field for discovering unexpected phenomena. Ultimately, cosmic rays teach us that the universe is far more energetic, dynamic, and violent than it appears through ordinary telescopes. They reveal a cosmos filled with exploding stars, colliding galaxies, turbulent magnetic storms, and unseen dark matter interactions. Through their compositions, energies, and arrival patterns, cosmic rays paint a vivid image of a universe constantly in motion, shaping itself through forces both familiar and mysterious. And perhaps the most profound lesson cosmic rays offer is that the atoms in our bodies, the atmosphere we breathe, and the structure of our solar system have all been shaped, in part, by the relentless rain of cosmic particles over billions of years. They tie us to the history of the galaxy and the universe beyond, reminding us that even the smallest particle arriving from space carries within it a story older than Earth itself.